Welcome back, grade 12s. Today we're going to take a look at section 2.1, Radical Functions and Transformations. As you can see, today we'll focus on investigating the function y equals the square root of x using a table of values in a graph. We're going to look at graphing radical functions using transformations, and we're going to find out how we can identify the domain and range of the radical function. You'll see on the right over here that a radical function is defined as a function that involves a radical with a variable in the radicand. So we've got a radical here with a variable, the x, in the radicand under the root sign. Or over here, 4 times the cube root of 5 plus x, and again the x is under the radical sign. So let's take a look first at example 1. So example 1 I've taken from your textbook, and it's the Your Turn section. So we're going to look at how we can graph a radical function using a table of values. And let's start with y equals the square root of x. And then we'll move on to y equals the square root of x plus 5. First, we need to identify the restrictions that are on y equals the square root of x. We should know by now that we can't take the square root of a negative number, so the restriction is that x must be greater than or equal to 0. We can take the square root of 0. Then we can create a table of values for that, for values that are greater than 0. Like 0, 1, 2, etc. Now, we can calculate the square root of 0. We know what that is. Square root of 0 is 0. Square root of 1 is 1. Square root of 2, we can calculate that as well, 1.41. And the square root of 3 would be 1.73. But these values are inconvenient. We can calculate them, but they're inconvenient, unlike values of the square root of a perfect square. So we're going to continue with numbers like 4 and 9 and 16 and 25 because they're convenient for us. They're easy to do. We can calculate the square root of 4 and 9. The square root of 16 is 4 and the square root of 25 is 5. Once we have the table of values, we can go ahead and plot the points on a graph. So 0, 0, for example, plots right here. And 1, 1, over 1 and up 1. 2 and 1.41, that's about here, and 3 and 1.73, that's about here. But you can see there it's an approximation. It's not super convenient. The rest of these points, however, are bang on. Over 4 and up 2, over 9 and up 3, over 16 and up 4, and I could go to over 25 and up 5, but I run out of room. And some of you may recognize that as sort of half of a sideways parabola. If you imagine going over 1 and up 1, or over 2 and up 4, over 3 and up 9. The domain of the radical function, so we've got the domain would be all the x values such that x is greater than or equal to 0, where x is an element of the set of real numbers, and the range is all the values of y, such that y is greater than or equal to 0, because this keeps going higher and higher and higher, and where y is an element of the set of real numbers. Now let's repeat the process with y equals the square root of x plus 5. First, we can identify the restriction as x plus 5 must be greater than or equal to 0, and that means that x must be greater than or equal to negative 5. We can build a table of values again, but this one's going to be a little different in order to help us out. We're going to have 3 columns in this table of value. We'll have an x and a y, but we're also going to have the x plus 5. Now, x plus 5 is the piece that's under the radical sign. If x plus 5 is equal to 0, then we know that y is going to be equal to 0. And if x plus 5 is equal to 1, then we know that y is going to be equal to 1. If x plus 5 is equal to 4, or 9, or 16, or 25, we know what y is going to be. The question is, what is x going to be? Well, what's the value of x such that if I add 5 to it, I get 0? And we know that that has to be negative 5, because negative 5 plus 5 is 0. And negative 4, because negative 4 plus 5 is 1. And negative 1, because negative 1 plus 5 is 4. And 4 plus 5 is 9. And 11 plus 5 is 16. And finally 20 plus 5 is 25. So this is my set of coordinates. At negative 5, 0, I'm going to have my first point. At negative 4 and 1, I'll have another point. At negative 1 and 2, at 4, 3, at 11, 4, at 20, 5. So I can connect those dots like I did before. You'll notice it's the same shape. All we've done is translate the graph, like we saw in Chapter 1, 5 units to the left. So that's how we can build a radical function using a table of values. Now, we're going to go further than that and apply transformations knowing that this is going to the left 5, and we'll be able to graph much, much quicker. Okay, so in much the same way that we transformed functions in Chapter 1, we can graph transformed radical functions when written in the form y is equal to a times the square root of b times x minus h plus k. And let's do that with example 2. In example 2, we've got y is equal to negative 2 times the square root of x plus 3 minus 1. It's a transformation of this function y equals the square root of x. So let's start first by identifying the values of a and b and h and k. Now the a value is always the one that's in front of the function, so in front of the square root function, and that's our negative 2. The b value is the coefficient of x, and in this case the coefficient of x is 1, so we're just going to write b equals 1. The h value is often added to or subtracted to the x. Now we have to be careful. If there's a b value, we have to factor that out of these two terms. But in this case we don't, and we see that h is negative 3. Remember that in the function, I'll just scroll back up here, in the function it's always x minus h. So if we see x plus h, we know that our h value is negative. And our k value at the end here, negative 1. So we can use those points and we can apply them to the coordinates of x comma y and then map the new coordinates of this transformed function. So a, negative 2. We know that the 2 value does a vertical expansion by a factor of 2, and it reflects in the x-axis. So that's going to affect our y-coordinate. It's going to make it twice as big and change the sign. So for a equals negative 2, we get x comma negative 2y. The b value of 1 doesn't change anything. So for our b value of 1, that would be a horizontal expansion or compression, and since there is none, our x value stays the same, and there's no effect on the y value. The h value of negative 3 means that it's a horizontal translation to the left 3, and that's going to affect the x coordinate, so we're going to have x minus 3, no change to the y coordinate, so negative 2y. And then finally our k value is equal to negative 1. That's going to be a vertical translation down 1, so that's going to affect our y coordinate, and we're going to have x minus 3, no change to the x there, and then negative 2y minus 1. So that's going to be a new set of coordinates, or the map to get the new set of coordinates. I'll just rewrite that here as x minus 3, comma, negative 2y minus 1. Now to graph the transformed function, one option, my preference, is to graph the base function first and then transform it using the map. So I would start with a set of axes. I'd plot my base function. I'll just do that in red. That's the square root of x. So 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, and 3, and 16, and 4. Then I'd write the coordinates down for each of those points and transform each of them using this map. So if I've got 0, 0, my new map takes the x-coordinate, moves it back 3, and then flips it over twice as far and down 1. So it moves it back 3, then it flips it over so it stays on 0, expands it by 2, stays on 0, and moves it down 1. So that's going to be my A prime. Point B here at 1, 1 goes back 3, flips it over the axis, makes it twice as far from the axis, and moves it down 1. C over here goes back 3, and then it flips over the axis, goes twice as far, and down 1. My next one, I might have trouble graphing this one. Over 9, or 9, 3, goes back 3, flips over the axis, goes twice as far from the x-axis, and down 1. And lastly, back 3, reflect, double, 1, 2, 3, 4, and down 1. C prime, D prime, and E prime. Let's just see if that makes sense. It's twice as tall, it's flipped in the x-axis, it's been moved to the left 3 and down 1. So let's see what happens here. It's twice as tall, double, double, and double. It's been reflected in the x-axis, so this comes to here. This one is 6, and this one is at 8. 8, move that down a bit, there we go. And then it's been moved back 3 and down 1. Yep, back 3 and down 1. Back 3, down 1, back 3, down 1. So the mapping part, as far as I'm concerned, is way more effective than doing all the multiple transformations one after the other. I find, though it works well, I find that some people get mixed up with that. Okay, so there you have it, graphing with the table of values and graphing with transformations. There's other examples in the textbook you can take a look at. Example 3, determining the function from a graph, and example 4 is an application of radical functions, but we'll look at that in class as well. Take care.